Temperature is a really important quantity that we haven't really talked about up till now, and temperature is going to be one of the things that we're focused on now from here until the end of the class. Right now we're not defining the details of what it is, but we're going to get to that very soon. Right now we can say that it is related to thermal energy, and previously we talked about thermal energy as a vibration of atoms or the molecules that a substance is made out of. And again, in general, we don't distinguish whether we're talking about atoms or molecules. So it's not equal to thermal energy, but it's going to be related to it. And it's going to depend on the material, and we'll get to all of those topics very soon. But temperature is related to this energy. You can think about it as kinetic energy of the atoms or molecules bouncing around in a substance. Now, the reason that temperature is interesting and why we're starting to talk about it right now is that many properties of a material are actually proportional to temperature. And here I clarify that this is absolute temperature, and I'll say what that means in a slide or two. But so these properties might include, for instance, electrical properties such as resistance or conduction properties. You can have expansion that is proportional to temperature, and we're going to see that there's a lot of state variables that are related to temperature, such as pressure and volume, depending on what else you have fixed. So in some cases they're not proportional but linearly related, but many are proportional, and that's very interesting. That allows us to actually measure temperature. So there are 3 temperature scales that we're going to talk about right now, and really you can define whatever temperature scale you want, but it's helpful to talk about ones that other people actually know about. Now, in the United States, many of us grow up using Fahrenheit, and so that's the one that we have some intuition for, but Fahrenheit's actually the worst to use for science, and the rest of the world doesn't know it. So Fahrenheit, we use degrees F, and we can convert, of course, to Celsius. This is a conversion many of us already know from when we were younger. Celsius, which is measured in degrees C, degrees Celsius, which also gets called centigrade. We'll talk about this as T sub C. The one that is actually SI units is Kelvin. Note that we just call this K. We don't call it degrees K. And one of the things that's helpful is that the interval between Kelvin and Celsius is actually the same. So if you increase the temperature by 1 degree Kelvin, that's the same as increasing it by 1 degree Celsius. So if you're talking about a temperature change, these are actually equivalent. Fahrenheit is not. Don't use Fahrenheit pretty much ever. However, if you want to talk about absolute Kelvin, absolute temperature, you need to use Kelvin. And here are 2 of the conversions that we typically use. Obviously, you can combine them together if you want to go from Fahrenheit to Kelvin. So let's think a little bit about the scale. And there's a few different temperatures that we frequently think about, but what we're going to complicate very soon is that this is at a certain pressure. This isn't actually uniform. So the most helpful thing to realize is that there's an absolute value. When we're working in degrees Fahrenheit or degrees Celsius, we can talk about negative temperatures. But when you're in Kelvin, there is no such thing as negative temperatures. Again, this relates to thermal energy, which is related to the energy that atoms have. You know that there's no such thing as negative energy if we think about something like kinetic energy. So absolute zero is zero thermal energy. It's zero motion. So this has a lot of meaning. Kelvin never goes negative. Celsius, Fahrenheit, those do go negative, but they do have an absolute lowest value because at that value, Kelvin is 0. Now, nitrogen is something that is liquid below 77 Kelvin, and so liquid nitrogen is something you frequently see in science centers. And then CO2, carbon dioxide, so this is, for instance, dry ice, that sublimates, meaning going from a solid to a gas at these 3 temperatures. Then one that you probably know is water freezing, 32 Fahrenheit, 0 Celsius, 273 Kelvin. So that's the easy way to remember this conversion. Now if we add on 20 degrees Celsius, that gives us to room temperature, and you see if you add on 20 degrees Kelvin, that gets us to room temperature as well. So that shows us that the delta in temperature is the same between Celsius and Kelvin, but the 0 point is different. Now then, water boils at 100 degrees Celsius, but 212 Fahrenheit. Again, converting this Celsius temperature by adding 273, we get 373 Kelvin. Note that again, water boiling is not actually a perfect calibration, and you can actually use any 2 points on this because this is a linear scale. So if I wanted to create a new temperature scale, I could actually do that by, for instance, maybe picking 0 degrees to be where nitrogen boils and 100 degrees to be normal body temperature. These are all linear scales, so that would still be a linear scale, and that would work as well. Okay. The physics meaning here that we actually care about is this idea that properties are proportional to temperature if we're talking about temperature in Kelvin, absolute temperature. And the example of this that we're going to dive into for some detail for a few chapters is actually the relationship between pressure, volume, and temperature for an ideal gas. So imagine that I have a gas that's in a rigid sphere, meaning that it's of fixed volume. And then we actually are measuring the temperature of, say, the surface around it, where we say that this gas is going to be in equilibrium temperature-wise with that surface. We then read pressure. We see that pressure is actually going to be linear with respect to temperature, and this is independent of what gas we use. So gas 1, 2, and 3 here could be, for instance, oxygen, nitrogen, and helium, perhaps. And so we get this linear relationship, and we see that as we decrease the temperature and decrease the temperature, eventually pressure would be going to 0. And that temperature at which pressure is 0 is our 0 degrees Kelvin, or negative 273, numbers are hard, Celsius. And again, pressure is a variable that can't be negative. So that's why talking about 0 pressure is interesting. So this is something that, again, this value isn't very meaningful in Celsius, but we would define this point to be 0 Kelvin, and we see that we have this linear behavior. So the idea of a linear behavior is if I, for instance, double my temperature when I'm measured in Kelvin, that would tell me that I've doubled my pressure. That relationship is not going to hold if you're using Celsius or if you're using Fahrenheit, which is why it's so important that you use Kelvin.